Hi everyone, welcome to this technical session. I am Alex Casalboni. I'm a developer advocate from AWS based out of Italy, and this session is going to be about performance and cost optimization for your serverless applications. We're going to focus mostly on Lambda functions. There will be another session by Chris Munns that will focus on serverless applications in general, so how to re-architect your applications, how to bring in other services, or what are the technical choices about architecting well-architected serverless applications. So our agenda today is really about covering the fundamentals, just to make sure everyone is on the same page with serverless, what we mean by that, what are the fundamental concepts to understand the rest of this session. And then I want to dive straight into the optimization best practices. Here we'll talk about cost and performance and cold starts and everything related to performance for your function as a service specifically, so your Lambda functions. And then I want to present a data-driven approach to solve some of the challenges related to function as a service optimization, and I'll also share some real-world examples and some sort of framework to think in terms of cost and performance patterns, so that when you're building new applications, you can more or less know what to expect, and you can optimize each individual function the best you can. So there is a related breakout, as I was mentioning. This is SVS 403 from Chris Munns. This will talk about everything that is around your Lambda function, so everything about serverless apps, the whole serverless platform on AWS. So let's get started. Fundamentals. This is how Werner Vogels talks about serverless, right? The idea is that we can focus on the business logic. We can focus on adding value and writing business logic only when it's necessary. So there is a lot you can do with direct service integration, but when you go and write a new function, when you go and build, design and build new business logic, that's where we want to focus our efforts as developers. And so what does the Lambda function look like? You've probably seen 100 different versions of this. We have a handler, which is basically the entry point of a function. In that handler, you get an event, you get the context. Nothing fancy here. You can implement whatever business logic makes sense to you there. You can use functions and classes and objects and modules and dependencies. You can almost do whatever you want. If you ask me 3 or 4 years ago, there were many more limitations. Now you're almost free to do whatever you want. You can use layers, you can use external libraries, external services. You have the SDK in there. But then let's have a look at the code. The typical structure of a Lambda function code. So typically you have your handler in there, that's the entry point, but then you also have other sections up there and maybe additional methods. Up there you usually have everything about configuration management and dependencies, any helper or parameters fetching, anything that needs to happen as soon as possible in the initialization phase. And up there, you can do a lot of shared configuration. Sometimes you also have multiple functions in the same file, and if they need exactly the same configuration, that's where you can do that. Then you have a lot of helper functions like pre or post handler, database connections, everything that enables your business logic to function in the first place. And then you might have the actual business logic functions, do A, do B, and then do C. And, the best practice is to kind of encapsulate and organize your code in a way that is readable and maintainable and testable. So in some languages like Python, you probably use modules, JavaScript as well. In other languages, you use classes on different files and you organize code however it makes sense to you. But this is a typical structure of a Lambda function, and there are already here a few things we can do to optimize. But then a serverless application is actually composed of multiple Lambda functions, right? Each one with its own configuration phase, initialization, handler, helpers, and business logic. If there is something that you can share across all these functions, you can use the Lambda layers. That's a pretty good way to optimize the development experience. It doesn't really add much to the real time, to the runtime performance of your functions, but it's really interesting that if you have a heavy library or a heavy dependency, you can share that in a centralized layer so that it's much easier to develop new functions based on those libraries or dependencies without having to upload megabytes and megabytes every time you want to do a little change in your business logic. So each of these functions will have its own invocation and execution lifecycle. So before we can run your code, there are a few things that need to happen. You need to download your code. We need to start a new micro VM. This is actually powered by Firecracker. I've got a t-shirt today. And then we can bootstrap a runtime. It could be a custom runtime that you provide, or it could be a runtime that Lambda itself maintains, like JavaScript, Node.js, Ruby, Python, Java, .NET Core, and so on. After that happens, we can finally start your code. And the first 3 steps are what we typically call a cold start, right? That happens when you're scaling out or after a while that you haven't been executing your function. And so AWS works every day, every week, every month to optimize the performance of the first half, actually even including the bootstrap. So let's say the first 3 steps of this life cycle, because those are parts under the hood of the system that we can optimize for you. There are things that you can optimize as well, and that's kind of part of the shared responsibility model that applies almost everywhere at Amazon Web Services. So you are responsible for optimizing your runtime if you're bringing a custom runtime, and you are responsible for optimizing and maintaining your application code, of course. So in this session, we're going to talk mostly about that last part, what you can do in your code to optimize the cold starts and what you can do to optimize all the rest of your Lambda function execution as well. If you want to monitor what's going on, there is a pretty easy and straightforward way you can enable X-Ray distributed tracing, and that will give you visibility into how the execution time of your function is spent. Was it a cold start or not? How long did, if you are using and invoking additional services like S3 or SNS or DynamoDB, you can have a look at how the time is spent inside each individual invocation. So let's get into the best practices. I like to categorize the best practices into 2 different categories. One for everything related to cold starts. So cold starts, as we just said, happens every now and then, and they can have an impact on the customer experience. If you're building latency sensitive or customer facing APIs, you do want to minimize the effect of cold starts. Although typically, unless it's a very edge case where you run your functions only a few times per day, typically cold starts are a very small percentage of your overall executions, probably less than 2, 3, 4, maximum 5% of your execution. So we want to maximize that, especially so that when we are scaling out and we have peaks of traffic, not everyone is experiencing a cold start, which might mean a few hundred milliseconds of additional latency. So the best suggestion I can give you to minimize the effect of cold starts is to not build monolithic functions. So a monolithic function is if the deployment package that you're building is like 25 megabytes of business logics, library and dependencies and shared objects and whatever you have in your deployment package, the more bytes have to go over the network for us under the hood, the more effect you can expect on the cold start. I'm not saying you should always build nano services where you have only 10 kilobytes of code or even a few bytes of very simple business logic without any dependency or any object. Pretty often you do need dependencies or modules. Pretty often you do need to have even heavy binaries or dependencies in your functions. So what I'm trying to suggest is to be mindful of what you include in your deployment package and try to shrink it to the bare minimum. For example, in some programming languages, you can try to minify or uglify, try to optimize the size of your code together with its dependencies. So you can do things like removing dependencies that you're not actually using in production and stuff like that. Another thing you can do, especially when you're working with dependencies and libraries that are modular, is that you can optimize the way you import them. So, for example, with the Node.js SDK, you can import only specific submodules instead of the whole SDK, and that will have a pretty interesting impact. And I'll show you an example in a second. You can reuse connections as much as possible across invocations. So if you are invoking APIs or if you're using the SDK, there are very simple ways to configure the connector or the client to keep the connection alive. And that sometimes can save you, the cost of reconnecting every time. If you're doing 2-3 calls, for example, to DynamoDB in the same execution, you probably don't see that. But if you are doing very simple CRUD operations, that's one way to save the cost. To reduce the cost of a cold start across different executions. 2 more things. You can use lazy initialization. If you're like me and you like to have multiple Lambda function handlers in the same file, sometimes you end up with initialization code that is only specific to one of these functions. And if you think about it, if you are executing the same initialization code for all the functions in that file, but some of those shared objects or libraries are not actually shared, you're just maximizing the cold starts of all the functions in that file. So what you can do is you can lazily initialize those not really shared objects and then actually initialize them down inside each individual handler. And I'll show you a simple example in a second. The last thing, you can use provision concurrency. So this is a pretty straightforward way to get rid of cold starts in a managed fashion. So instead of using CloudWatch events to try to keep your functions warm manually, or instead of trying to guess how much concurrency you're going to need, you can configure provision concurrency with auto-scaling, and you can, especially for those use cases where you can predict how much scale you're going to need, how many concurrent API calls or executions you're going to have, provision concurrency is pretty useful, a mechanism to basically get rid of cold starts. So your pre-provisioning environments that are going to be warm for you as long as you need them. Let me show you a few examples. So this is a simple example of lazy initialization, where we have 2 functions and 2 shared objects, but the shared objects are actually used only by those 2 individual functions that are not actually shared. So this doesn't really have a huge impact with the AWS SDK objects, but imagine that maybe you have other heavier libraries that take 10, 20, even 100 milliseconds to initialize those objects. So what you can do is you can initialize them as none or null or whatever makes sense in your programming language, and then you actually initialize it inside the handler. Optimize dependency usage. This is pretty common, especially for Node.js. If all you're doing, for example, is using the DynamoDB client inside your functions for simple CRUD operations, instead of importing the whole SDK, you can just import the DynamoDB module. And that sometimes will save you up to 100+ milliseconds. Again, we are talking about cold start. Not much changes, actually nothing changes for the largest majority of your function executions. But if you are concerned about minimizing the impact of cold starts, I think this is one of the very easy low-hanging fruits to improve the situation if you're using Node.js. And this is thanks to our Serverless hero, Yan Chui, that did pretty interesting research on the topic. You can find the article in the bottom of my slides. last thing I already mentioned, provision concurrency. Keep in mind you shouldn't need to change anything in your code. It already integrates with AWS autoscaling, so you don't really have to know in advance how much provision concurrency you need. You can let the autoscaling do its job and go up and down depending on demand. And this might help you especially improve the user experience and the customer UX. Also keep in mind there is a ramp-up time of about 500 runtimes per minute. So if you need, I don't know, 5,000, it might take up to 10 minutes, about 10 minutes to spin up those environments for you. And any invocation above that number that you configure in provision concurrency, you're going to be charged the regular amount. Okay, so you do not get throttled or anything. Now, let's get into the second category, which in my opinion is even more important, because optimizing cold starts is great, and you want to do that especially for latency sensitive and customer facing applications and functions, but sometimes I think you want to focus your energy on optimizing the largest majority of your execution. So here there are a few things you can do related to both performance and cost. So first tip for you is try to not do a lot of orchestration inside your function. If all you're doing is call this API and then wait, or start a batch processing task and then wait for it to complete and then start this other thing. If what you're doing is orchestration, you can do a lot of that orchestration much cheaply and efficiently by using something like AWS step functions, which is also language agnostic and allows you to build functions that are more, one purpose, very simple business logic there. Another tip is try to use Lambda functions to transform instead of transporting data. So there are a lot of situations where you want to fetch a lot of data from services. Could be S3 or could be a database, like you do in a database where you run, an SQL query with a where condition. So you want to only filter some of the data that you want to fetch out of the database. You can do the same with other services like S3. So you can say S3, don't give me the whole object, just give me a small part of it or a small subsection of the objects, of the JSON objects maybe inside an S3 object. So there are many ways you can optimize that, and I'll show you an example in a second. The other thing is you can discard events that are not interesting as soon as possible. So if you're using triggers like S3 or SNS for your functions, you can configure those triggers to not invoke your function if the object, for example, if you only want to process images like PNG and JPEG and not PDF files from S3, why should you invoke a Lambda function to do if it's JPEG or PNG? Go on and do the business logic. You don't even want to do that. You don't even want to get your functions invoked, so you don't pay for it, right? So try to discard uninteresting events as soon as possible. Another tip is try to fine-tune the resource allocation of your function. You have the memory that you can tune in your functions from 128 megabytes up to 3 gigabytes of memory. So try to not guesstimate how much memory you need, but also try to remember that memory is not just memory, and we'll talk about that soon. Lambda destination, it's not really a way to save a lot of money, it's a way to automate the delivery of the output of your functions to downstream destinations. I think sometimes it might actually help you save some money because you're not just sparing some code, getting rid of some code in your business logic. If you need to publish a message on an SNS topic or put a message on an SQS queue, it's not just code that you need to write, but it's also execution time of your function that you don't need to pay for. So if your execution time is pretty close to 100 milliseconds and you want to go down one level to less than 100 milliseconds, sometimes using destinations allows you to shave off those 10, 15, or 20 milliseconds that are needed to put the data where it needs to be. Also keep in mind the try policies. They don't really allow you to save money here, but it's something very important to keep in mind because they are super powerful. You often need them, and you can configure how many retries you want for asynchronous executions, but they are not free. So be mindful, configure them, or set them to 0 if you know very well that you don't need them. Let me show you a few examples. This is how the function looks like. I talk about orchestration. You define your state machine in JSON format. This is Amazon States language. You can visualize it in the console or even in your IDE. For example, for VS Code, you can just visualize it without leaving your IDE. And then you can monitor executions in the service user interface or even via API. This is an example of transform instead of transport. So this is an example where we are iterating over a lot of S3 objects, and we were downloading all those objects and then just fetching the first 8 bytes for whatever reason. I think it was trying to read an IP address from a record. So instead of doing that, just by changing that logic and using Amazon S3 select functionality of S3, that allows you to do like let's say an SQL query to fetch subsets of an object. You know, the execution time was less than a half, and it was 4 or 5 times cheaper overall. So pretty interesting use case there, where you can delegate the processing or the filtering to the upstream service like S3 or like you would do with a database. But let's go back to our step of the optimization. If you look at them, what you realize is that most of these techniques kind of force you to re-architect your application or to rethink about how I'm using the service, how I'm doing orchestration, how I'm configuring my triggers, how I'm sending data around. There is one of these techniques that actually don't force you to change anything in your code, and that is fine-tuning resource allocation. And believe me or not, I hope you believe me, and I'm gonna prove it, you can achieve a lot just by fine-tuning the resource allocation. Because as I mentioned before, when you fine-tune the memory of your functions, you're actually fine-tuning the power of your function. So for the rest of this talk, I am going to talk about power instead of memory. When you give your functions more memory, you get more CPU, you get more I/O throughput, you get basically more everything. You get a more powerful machine under the hood. So let me show you an example. This is a CPU-bound example, and it works specifically with CPU-bound examples, but not only. Let's say we are computing prime numbers. This is very CPU-intensive. If we start with 128 megabytes, it takes more than 10 seconds. If we use 10 times as much memory, up to 1 gigabyte, it will take 10 times less, almost 10 times less. And the cost is pretty much the same. So let me show you that visually, okay? We'll see a lot of these charts. Let's imagine that the red line is execution and blue line is cost. So execution time, red, execution cost, blue. As you can see, when we add more power, and that you see that on the x-axis, you know, from 128 up to 3 gigabytes, the execution time goes down very quickly. The interesting bit is that sometimes, while the execution time improves, the cost is being pretty flat, and sometimes it's even decreasing, like in our prime numbers example here. So there is no reason to not use more power or memory, right? We can be faster and cheaper at the same time. I believe this is quite a game changer for a lot of use cases, especially, again, if you have a CPU-bound workload. Now, I'm very passionate about this topic, and especially back before I joined AWS, I was an AWS customer, and I use Lambda a lot, and one day I was there trying to fix this problem, and I had an idea. I had a data-driven idea. What if I can use data to solve this problem for everyone? So I started building, and I'm still building and maintaining a project called AWS Lambda Power Tuning. It's basically a state machine powered by step functions that takes your function in input. It will run it a few different times based on the configuration, based on a few parameters that you can control, and then it will provide as output the optimal memory configuration for your specific function. So you can integrate it with CI/CD pipelines. It's completely open source. It's available on the serverless application repository, and you can literally deploy it in 30 seconds with a couple of clicks. So have a look at it. How do you use it? You can provide an input where you specify your Lambda function arn, the power values that you want to test. You specify the number of times that you want to execute your function and what is the payload. This could be a fixed static payload, or you can even specify multiple payloads with a weight. So there are a lot of more options that you can find in the documentation. It would be too long to put on this slide. What can you expect in the output? In the results, you get the optimal power and the optimal cost and average duration for corresponding to that power. But then you also get some metadata about the state machine execution itself. So how much did you pay for step functions? How much did you pay for Lambda? And also, most importantly, you get a URL where you can visualize the results. So I'm going to show you a few examples. What I would like you to get away from these examples is that there are multiple patterns depending on what your function is doing. Is it CPU bound? Is it network bound? Is it talking to a database? Is it talking to an external API? Is it downloading data from Amazon S3? What is it doing? And depending on that, how does the cost and performance pattern change? Which means, in a way, which functions are more worth optimizing. So let's get there. Let me show you a few examples. So the typical function that a lot of us are building every day are the no-op functions. These functions do not call an API, do not do any long-running processing, do not invoke any AWS service. These are just taking the event, the input event, and doing some trivial data manipulation on it. Typically take less than 100 milliseconds. So based on Lambda's pricing, what happens is that there is no way to make these functions cheaper, right? As you can see, the blue line always goes up, and what is there to optimize? Well, maybe the performance. Maybe we would like to have some of these Lambda function execution faster. So it's interesting to see that if you move from 128 to 256 megabytes of memory, you can sometimes see a pretty interesting improvement in latency, in execution time, maybe from 5, 10, or 20 milliseconds down to 1, 2, or 3 milliseconds. So this may not be super interesting for a RESTful API, but if you have, for example, a microservices system where you have multiple small functions interacting with each other and coordinating with each other to maybe provide a response back, if you can shave off 5, 6, 15, or 20 milliseconds of each one, you might end up with something that is meaningful even for the final user of your APIs. CPU bound example, this is not the prime numbers example I did before. This is using NumPy. I was doing some a large matrix multiplication. I believe it was a 1500 by 1500 matrix inversion or multiplication. And as you can see, it's pretty impressive that we can go from about 10 seconds down to less than half a second. And the most interesting part is that for these CPU-bound workloads, typically the execution cost is pretty flat. So you can get almost 10 or sometimes even 15 or more x better performance for a cost that is usually comparable, or maybe 10 or 15 times, 10 or 15% higher. So it's a trade-off. If this was a RESTful API and you were to decide between 9 seconds and 400 milliseconds for 10% more price, would you go for it? Personally, I would. I think the best part is that this data allows you to take a data-driven and an informed decision. If you go back to the prime numbers example, we see that, as I said before, here the execution cost is not only flat, but it's actually going down a little bit. So there is no absolute reason for not choosing 1.5 gigabytes of RAM here, because we're going to be faster and cheaper at the same time. We go from 35 seconds to less than 3 seconds, basically for 5 or 10% cheaper. So why wouldn't you do that? If you find a good reason to not do that, please let me know on Twitter, on LinkedIn. I want to know why. Let's go into the network-bound examples. Let's imagine we're calling a third-party API. So here, usually you really can't do much to speed up the third-party API. Whatever power you have, however fast or powerful is your function, you can't really affect something else out there, especially if it's an API out of the AWS data centers, wherever it's hosted. So as you can see, the execution time this time, the red line, is pretty flat. So whatever we do, execution time doesn't change, while, as you would expect, the execution cost always goes up. So here we can't really do much. My suggestion is try to stick to 128 megabytes, unless you are uploading or downloading a considerable amount of data, more than just a couple of kilobytes. In that case, you might see better performance, maybe 10 or 20% better execution time performance, and so the cost might be good enough for you to decide to increase power a little bit. But my suggestion is try to take a data-driven decision, so you're not guesstimating. Another example with DynamoDB queries this time. Imagine you're doing 1, 2, 3 DynamoDB queries in a row. What typically happens is that because you're not paying the cost of instantiating the connection every time, unless you're using Keep Alive, you can see a pretty interesting benefit in adding more power. So with, for example, half a gigabyte, 512 megabytes, we can see that we are basically paying the same as 128 megabytes, but we are almost 7 times faster, about 50 milliseconds instead of 350. So that's a pretty interesting improvement for the same cost, so go for it. On the other hand, if you're downloading a lot of data from S3, this is not a recommended workload. Now you have even EFS support, but if for any reason you need to download a lot of data from S3, it's a similar pattern to the third-party API. So execution time is pretty flat, and the cost is always going up. But because we are downloading a lot of data, we might be able to exploit the multi-threading nature with some programming language, and the fact that above 1.8 gigabytes, you actually get 2 virtual cores with Lambda. So with multi-threading, you can do a lot better. This is what it looks like with multi-threading. So we are a lot faster than we were even with the maximum power in the previous slide. And also, as you can see, the execution time is going much better. And the cost has an interesting curve where you can take a trade-off decision based on your business requirement. Are you okay with paying 30 or 40% more if you can be, as usual, 3, 4, 5 times faster? This is a business decision, usually, not just a technical decision. So consider your requirements, consider your SLA, consider your performance goals, and try to understand whether, sometimes increasing your Lambda bill from $20 to $35, so pretty substantial increase, almost 100% increase, but maybe you can get twice as much performance out of your function. So is it worth it? That's up to you to decide. I'm trying to provide you a tool so that you can take the best informed decision. Now, keep in mind there are different patterns. My suggestion is try to experiment with Lambda power tuning. Try to have a look at these charts. Maybe try to use it with some of your functions, get experience with the different patterns. If you find a new pattern that I haven't documented, please let me know so I can include it in my presentations. So takeaways. We've seen how to optimize function as a service in general. Keep in mind what you're trying to optimize. Keep in mind you can avoid cold starts with a few different techniques, plus provision concurrency that is a managed way provided by the Lambda team. Remember that memory actually means power with AWS Lambda, and in my opinion, the best way is to always think in terms of workload categories and these cost performance patterns that I have shared with you today. If you want to visualize the different trade-offs, you can always use Lambda power tuning. It's open source on GitHub. Feel free to open issues, feel free to contribute, and let me know what you think. Thank you everyone for watching, and enjoy the rest of the event.